Okay, so now we're ready to begin the main material of the course, and that is in this second unit of the course, which is understanding what are the basic building blocks of the world around us. Now, we have to start, scientifically somewhere. I have to assume some type of background when I begin. So this first part of this unit really isn't formally material for the course. This is just the background that we're going to be assuming that I'm going to be reminding you of. And this key piece of information actually comes to us again from one of the ancient pre-Socratic Greek philosophers. This would be Democritus, who of course is famous for the idea of democracy, but he's also quite famous for the idea of the atom. This idea that for any material, there must be a certain minimal unit of that material that has that material's properties, right, but that then cannot be further subdivided. I think it's some very interesting philosophical reasons why this could be the only coherent way to understand the material world around us. Now, the scientific background for this in modern science goes back to Dalton. And the story with Dalton actually is a little mixed, a little sketchy. He may have, added some things to some articles later on after he'd written them. And he was working just around the same time, of course, also as Avogadro, right? Who published a very interesting piece of work in 1811. And this is all sort of the basic chemistry background that I assume your I'll be assuming your chemistry teachers have convinced you scientifically of all of this, of how we know the atoms exist. Remember, this has to do with the observations of masses and densities of gases and how they tend to combine together in very specific ratios, where we notice there are, discrete ratios in compounds when we form molecules, things, for instance, like H2O. That was some of the evidence that told us that we had the existence of these atoms. Now, the other interesting thing here is that although they knew what the atoms were, right, they had no idea of what their atomic masses were, of the atomic masses in an absolute sense. But because they had this rule of combination, they knew the relative masses of the atoms. They knew the atomic mass ratios. And that's where you get this whole idea, right, of the mole, and where we think of 1 gram equivalent of hydrogen, for example, right, is sort of the basic unit of mass involved here. So we knew the atomic mass ratios, but we didn't actually know the absolute values of these atomic masses, but we were pretty darn sure there were these identical atoms corresponding to each particular element. Now, the story gets a little more interesting, actually, with another hero of ours from a previous course, who would be Faraday, who's famous not only for Faraday's law, but Faraday also published a very important work on the rules of electrochemistry. He did a lot of electrochemical experiments as well. Now, once we knew there were atoms, these electrochemical experiments, this was published in 1834, revealed quite a lot, a surprising amount actually, about the structure of matter. So the basic idea here in an electrochemical experiment is you're going to have some kind of a beaker, right, that's going to be filled with some kind of a liquid, some kind of an electrolyte, and you're going to put some sort of salt in there, maybe some metallic salt, say something like sodium. Not sodium. Let's say we take copper, right? And we now know from the modern point of view that when we put the copper in here, right, one of its electrons gets stripped off, and they actually exist in here as positive copper ions. Now, what they were able to observe macroscopically, they have now this idea of the atom. What they were able to observe macroscopically is a very interesting effect in an electrochemical experiment. So in an electrochemical experiment, you would do something like this. You would have a cathode. It could be perhaps made out of platinum. It's going to be my cathode. And it's a cathode because I'm going to connect it in a circuit with a voltage that I'm going to apply so that there will be a current flowing. And I will also connect that to some counter electrode known as the anode over here, and I'll put the positive side of the battery on that one, the negative side of the battery on this one. So then a positive current will flow in the external portions of the circuit from the cathode all the way around here to the anode. And when you do an experiment like this, something very interesting happens, right? We know that we have these negative charges that are flowing onto this platinum electrode, and as they do that, and it becomes negatively charged, it attracts these copper atoms that are in this charged state, and they begin to come down and they deposit very nicely, forming a nice little copper film on top of my platinum electrode. So there's a series then of conclusions and observations that can be made from this. So here are some interesting observations that were made from this type of a setup. Now they knew which way the positive current was flowing, right? So they knew then that it appeared that for most cases, in particular for metals, so for most metals, for example, for most metal atoms, and also quite generally for different elements, what you tend to find in these experiments is that you have positive ions because they come down then on the cathode. And because those are positive ions, what it seems to indicate is that there must be removable negative charges in atoms. Well, that's certainly a very interesting fact. So there's some component of these atoms that we can remove from them to form our ions. Okay, that's one of these key observations. The other key observation is we can start to get a little quantitative about this. So, for example, you can look at the charges and masses involved. We know, for example, in an experiment, the total amount of charge that comes down with our ions, right? Because that's simply the current that we had flowing in our circuit, which we could measure, times the amount of time, delta t, during which we did this deposition. And then we can actually measure how much the mass changes on the electrode before and after the experiment. And combining those two, then we can compute the charge to mass ratio of these atoms, because we now know there are atoms, of these atoms that are coming down. And when we compute that, there are two very interesting findings that we find. The first is that the delta Q over delta M is fixed and constant for each type of ion. Now, that's very interesting and important because since we have good reason to believe that the atoms that these ions are formed from, right, all have fixed atomic masses, the fact that this ratio is fixed tells us that the amount of charge on all of these ions is also fixed. Right, now I'm simplifying the electrochemistry here, right? You can also get doubly charged ions and so forth. But just putting that aside, this very fixed value, no matter how you do the experiment, tells you that there's a specific property of these atoms, which tells us that we can remove the negative removable part, the removable negative parts come in discrete packets or in discrete amounts. That's very interesting, right? You can't just like pull an arbitrary amount of negative charge, like it's some kind of fluid that you could abstract from the atom. It clearly comes in these individual units. The other interesting thing is the magnitude of this charge to mass ratio. We're going to do something with this later on, right? But since everything seems fixed, right, this total delta Q over total delta M, we know should match the charge to mass ratio on each individual ion that's coming down. And if you look at the value of that, for example, for the lightest element, right? Because they knew the relative masses of the elements. So the lightest element would be hydrogen, right? And you can do an experiment with hydrogen ions and evolve hydrogen gas. That charge to mass ratio turns out to be about 96 million coulombs per kilogram. And in a little bit, we'll see exactly here why this is important. Now, the final piece of this, now that we can get quantitative like this, where things become also very intriguing, is when we look at the charges on different types of ions. So, for example, you could take the charge to mass ratio of one type of ion in an experiment and look at the charge to mass ratio of a second type of ion, right? Which, of course, would be, as we were just saying, it's the charge to mass ratio of the individual atoms, Q2 over M2. And the intriguing thing is, although we don't know what the absolute masses are or the absolute charges, when we form this ratio, we're getting information about the charge ratio between the ions. And in particular, if I multiply this by M1 divided by M2, you see that I have a direct measure of the relative charges on two different ionic species. And it turns out that this always seems to be the same. Again, I'm oversimplifying. You can have doubly charged ions. So it can also come in simple fractions of each other. But the fact that these come out to be the same, or simple fractions, indicates very strongly, right, that this discrete unit of charge, so that implies that this discrete charge unit is universal, meaning that it is the same for all different atoms. So it seems like it's some universal type of negatively charged unit that can be removed from any atom, right? It's universal. It's the same for all atoms. Okay, so this is very intriguing evidence. I think you can put all of this together and come to the idea of something very much like the electron from these electrochemical experiments. But really put the nail in the coffin, and who really gets the credit for the discovery of the electron is J.J. Thomson. And we're going to look at that when we begin our first formal unit of this course.